This video is on section 8.1 notes, basic concepts of hypothesis testing. So this chapter is the culmination of statistics. This is where all of the units come together. First, we're going to introduce the structure of hypothesis testing in this unit, and then we're going to do the different types in 8.2, 8.3, and 8.4 based on the different population parameters. So today we're going to talk about all the different components of a hypothesis test and how they work together to give us information so that we can make an educated conclusion. So first we have some vocabulary terms to look at. We have hypothesis, a claim or a statement about a property of population, a hypothesis test or a test of significance. I'll use the terms hypothesis test, which is a procedure for testing a claim about a property of population. And when I say property of population, what I mean is the value of the population parameter. So a hypothesis is a claim or a statement about a population parameter, and a hypothesis test is where you're testing a claim, a population parameter. A null hypothesis, H sub 0, null hypothesis, is a statement that the value of a population parameter is equal to some claimed value. This is usually a commonly held assumption. And it's important that we notice that it said equal to. We will always use the symbol equal whenever we write our null hypothesis. Next, we have our alternative hypothesis, H sub A. Your textbook also uses H sub 1, so you'll see that in some of the screenshots that I put in these notes. This is a statement that the parameter has a value that somehow differs from the null hypothesis, and this is usually the hypothesis that the researcher wants to support. So we, for these, are always going to use the symbols less than, greater than, or not equal to, because we want to see something that's different than the hypothesis, which is equal. All right, so some examples of property of population so that you know what I mean by that, and if it's written, how to write those out. And again, population parameters. So if the statement says most internet users, like more than half, utilize two-factor authentication to protect their online data, then we're talking about a population proportion here. We're not talking about mean. We're not talking about standard deviation. So I would use the variable p, and I would say p is greater than 0.5. More than half is more than 50%, so greater than 0.5. The mean body temperature of humans is less than 98.6 degrees. So since we're using mean, we're going to use the variable for mean with the population, which is mu. Mu is less than 98.6 degrees Fahrenheit. The population of college students has IQ scores with a standard deviation equal to 15. So standard deviation of a population is sigma. So sigma equals 15. So those are just different ways you could write the property of population or write the population parameter based on how the statement is phrased. All right, so the whole purpose of this section is to go through a formal hypothesis test procedure, and there's 8 steps listed out, and we're going to go through all 8 steps with an example so that you can see how they work. So this example says, survey results show that 52% of 926 internet users utilize two-factor authentication to protect their online data. Does the data indicate that most internet users, most meaning more than half, utilize two-factor authentication to protect their online data? So does it prove it? Does it not prove? First step is to identify the claim to be tested and express it in symbolic form. So the question is, does the data indicate that most internet users, more than half, utilize two-factor authentication? So we want to know if the population proportion is greater than 50%, or greater than a probability of 0.50. Next, we're going to give the symbolic form that must be true when the original claim is false. So the opposite of this would be that the population proportion is less than or equal to 50%. Instead of being greater than 50%, it's less than 50%. And then from there, we identify what our null hypothesis is and what our alternative hypothesis is. So one of these is going to be the null, one of these is going to be the alternative. The null hypothesis is always the one that has the equal sign, and it can only be the equal sign. So this is going to be the one that we get our null hypothesis from. So we're going to say the population proportion is exactly 0.5. And the alternative hypothesis is going to be the other one. So p is greater than 0.50. All right, next step is to select the significance level. So the significance level alpha, this is not new to us, we've worked with this before, but the significance level for a hypothesis test is the probability value used as the cutoff for determining when the sample evidence constitutes significant evidence against the null hypothesis. We talked about significant evidence that something was unusual when we talked about outliers. And we used an alpha value of 5% or a probability of 0.05. And that's typically what we're going to be able to use here as well, unless they give us a different value. So it says, by its nature, the significance level alpha is the probability of mistakenly rejecting the null hypothesis, so doing something wrong or getting like an outlier answer when it is true. So the significance level alpha is the probability that you reject the null hypothesis when the null hypothesis is true. So we're going to use alpha equals 0.05. Only because they didn't give us a significance level, and so we're going to go ahead and use kind of the default. All right, on to the next step. So you don't have to read the top part again. I just kept the example problem at the top of the page so you can refer back to it if you need it. This says to identify the statistic, the sample statistic, that is relevant to the test and determine its sampling distribution. So in chapter 7, we talked about standard normal distributions, t-distributions, chi-square distributions, and we found test statistics from those, and we use these different formulas. So now what we want to do is we want to identify, based on the information given, which of these formulas would be appropriate. So for this example, we can already tell because they gave us the population proportion. They were talking about a proportion here. They were not talking about a mean. They were not talking about a standard deviation. We can already tell that we're going to be using the normal distribution and z-scores. We're going to be calculating the z-score. Now, there's requirements here, and for the most part, you're not going to run into problems that don't have the requirements met, but we can still look at this and make sure that the requirements are met. So I'm going to identify what the different numbers are in this problem. So we have the sample size is 926. We have p hat, which is the sample statistic, so 52%. We don't need it for the formula, but I'll say it anyway. Q hat is the complement of P hat. That's 48%, or a probability of 0.48. P is the population proportion, so that's 50. And then Q is the complement of that population proportion, and that's also 50. Okay, so here they just say that n times p has to be greater than 5, n times q has to be greater than 5. Of course, if we take 926 and multiply it by 50%, we are going to get a number that's greater than 5. And so we've definitely met the conditions to be able to do this sampling distribution and use this test statistic. So here we're going to say that we have a population proportion and so we're going to be using a normal distribution with a z-score. All right, step 6. is to find the value of the test statistic. So find the z-score. So I'm going to go through and write down all the information that I need. So I need the sample size. I need p hat. I need p and the complement of p. I think that's all I needed. Okay, so the z-score is, I don't know if you can hear my dog, but he's growling. The z-score is 0.52 minus 0.5 over the square root of p times q, so 0.50 times 0.50 over the sample size, 926. Okay, so I'm going to type this in. I like to type this in as a fraction because it looks like a fraction on my paper. And so I'm going to type alpha, the green button, and then y equals. So I have 0.52 minus 0.5. And then I've got that square root. So the square root is right here. So I'm going to hit the blue button first, square root. I have a fraction again, so I'll do alpha y equals again. And I have 0.5 times 0.5 over 906. All right, 1.217. Z-scores, we like to have 2 decimal places, so I'm going to do 1.22. Okay, so I'm going to go ahead and label this on this picture. So we had an alpha value of 0.05. So alpha is 0.05 right here. And if you recall, when you have an alpha of 0.05, I think this is from the section 7.1 notes, that corresponded to 0.95. And that was a z-score of 1.645. But I'll show you how we can find that. So if I have an alpha of 0.05, that's over here. And I know that the area is measured from the left instead of measured from the right. So if my alpha is 0.05, then I know that what I'm actually going to be looking for on here is 1 minus 0.05. So I'm looking for a z-score that corresponds to a 0.95 probability. And when I look for a 0.95 probability, it's right in between these two values right here, which is 1.6, and it's in between the 4 and the 5. So it's 1.645. Okay, so 1.645 is the z-score right here. I know that the middle in a standard distribution is a z-score of 0. And for my value right here, for my test statistic, I just got a z-score of 1.22. So my z-score is somewhere in here. Okay, so before I go much further, I'm going to look at some of these definitions down here because I think that they're going to be helpful as we kind of interpret what this means. So the test statistic, that 1.22 that we just found, is a value used in making a decision about the null hypothesis. That's what we're going to use it for. It's found by converting the sample statistic, in this case the p hat, converting the p hat to a score, in this case a z-score, with the assumption that the null hypothesis is true. That's what we're trying to figure out right now. The rejection region, or critical region, is the area corresponding to all values of the test statistic that cause us to reject the null hypothesis. So this right here represents that alpha of 0.05, that probability that we are wrong, or not that we are wrong, but that the null hypothesis is wrong. So this is the rejection region right here. Right? The critical value is, in a hypothesis test, these values separate the rejection region from the values of the test statistic that do not lead to rejection. So this is the critical value. It separates the rejection region from the region where we would not reject the null hypothesis. And then the p-value we haven't calculated yet, but it's the probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from the sample data, assuming that the null hypothesis is true. And we'll get to that in a second. So with this is our rejection region or our critical region. Our answer was over here. So that means we didn't run into a test statistic that tells us that the null hypothesis should be rejected. That's what this means. We ran into a number that said, like, yeah, this is the probability that it could be a value that makes it true. And it seems like, yeah, it's possible. It's quite possible. We didn't prove that the null hypothesis is true, but we didn't prove it false either. All right. And one thing I want to mention is that when you are dealing with your alternative hypothesis, they put H sub 1 here, I put H sub A, is that your alternative hypothesis can help you determine how to draw this distribution and how to interpret it, how to decide if it's a right tail or a left tail, or if it's going to have two tails. And we'll look at an example of that before this video is over. So in this case, because we had that our alternative hypothesis was that P was greater than 0.5, that's why we had this part over here is where our alpha was, what represented our wrong answers, right? So that's something to keep in mind. All right. So we had our test statistic. Our test statistic at this point is telling us that we're not going to be able to reject the null hypothesis because our test statistic was in the okay range, right? So next, we're going to say with the p-value method of testing the hypothesis, we make a decision by comparing the p-value to the significance level. And the p-value we calculate by finding the probability that the z-score that we found is greater than or less than or not equal to. It depends on how we set up the original hypothesis. We want to see the probability that that z-score is greater than, less than, or not equal to what it was. And so here we had our alternative hypothesis was that the p-value is greater than 0.50, and so we want the probability that our z-score is greater than 1.22 because that was the z-score that we found. So all I'm doing is I'm testing to see the probability of this happening, but I don't have a distribution table that tests the probability of p-values. I have a distribution table that tests the probability of z-scores. And so that's what I'm going to be looking up right now. Now, if I look at this table, my standard normal distribution table, and I'm looking for 1.22, I'm going to find it on this side. 1.22 is this value right here, 0.8888. The only problem with this is that for the picture that I'm working with, we had a shaded area on the right. We're looking at something that's greater than. So this is a shaded area on the right. And my table does the shaded area from the left. So I need to find the complement. So I'm going to say this is 1 minus 0.8888. And that's going to give me the probability. So by default, the probability that I would have found on this table would have been the probability that z is less than 1.22. And I wanted the probability that z is greater than 1.22, so I have to find the complement. So 1 minus 0.8888 is 0.1112. Okay, and we make a decision about our hypothesis and whether our null hypothesis should be rejected or not rejected by comparing it to the significance level. So 0.1112, this is our p-value, is greater than 0.05. This is our alpha value or our significance level. It is greater, okay? Now we make the decision to either reject the null hypothesis or fail to reject the null hypothesis by looking at these two rules. If the p-value is less than the significance level, then we reject the null hypothesis. And you can remember that by saying if the p is low, the null must go. If the p-value is greater than the significance level, then you fail to reject the null hypothesis. And in this case, our p-value was greater than the significance level, and that supports what we found on the previous page. Let me grab my previous page. I put it off to the side. Right here, that our z-score was in a normal range. That the value that we had was in a normal place. It was not in the rejection region. So we're going to say that we fail to reject the null hypothesis. So we have made the conclusion of our hypothesis test. This is our conclusion. At this point, we need to restate our conclusion using simple and non-technical terms because we want to have it be something that the standard layperson could read and understand what we mean. So this diagram gives you a way where you can write a sentence that the average person could understand. So if we start this, it says, does the original claim contain the condition of equality? So based on the way that the question is phrased, does it say that we have to equal something? So this says, does the data indicate that most internet users, more than half, utilize two-factor authentication to protect their online data? It doesn't say does exactly half. And so this is not equality. So our answer is no. We're going to go this way. And then it says, do you reject the null hypothesis, yes or no? We failed to reject the null hypothesis. And so this is how we're going to be phrasing our decision in non-technical terms. We're going to say there is not sufficient evidence to support the claim that most internet users utilize two-factor authentication to protect their online data. So there is not sufficient evidence to support the claim that most internet users use two-factor authentication. To protect their online data. Okay, so let's look at the steps that we did. We started off by reading the example problem and writing in symbolic form what they were trying to test. And then we found the opposite. We looked at both of those claims. We found the one with the equal sign, and we wrote that as the null hypothesis. And then the other one was the alternative hypothesis. We looked for a significance level. If it's not in the problem, we're going to use 0.05. From there, we looked at the population parameter that was listed in the problem, and we determined what test statistic we could use. If it's a population proportion, we're going to use a z-score. If it's a mean, we're going to use either a t-distribution or a standard normal distribution, depending on the information that's given. So either you do not know the standard deviation or you do know the standard deviation. Basically, that's going to be the difference. Well, yeah, that's the difference. Or you could have the population standard deviation, that's what you're testing, and then you're going to use a chi-square distribution. And that would be your test statistic. So that's what we look at next, is which test statistic are we looking at. Then we use the formula to find that test statistic. And at this point, we can compare our rejection region with our test statistic, and we can probably make a reasonable conclusion here. In fact, we can absolutely make a reasonable conclusion here based off of our test statistic. Our test statistic was not in the rejection region, so we failed to reject the null hypothesis. Okay, but there was another way for us to do this, and that was to look at the p-value. The p-value was the probability that the population proportion was greater than 0.50, which is the same as asking if the probability that the z-score was greater than 1.22. So we looked for that. We found the p-value was 0.1112. That p-value was greater than the significance level of 0.05, that alpha value. And because this was greater, we failed to reject the null hypothesis. So we looked at this, we said our original claim did not contain the condition of equality. The original claim was that most people, more than half, would use two-factor authentication. And so no, we did not contain equality. We failed to reject the null hypothesis, and so we need to phrase our question, phrase our sentence, interpreting our results this way. So those are the steps that you're going to do when you walk through one of these problems doing a hypothesis test. All right, so here is a diagram that just describes all the steps for you. Identify the claim, give the symbolic form, null and alternative hypotheses, significance level, test statistic. Now, there are two different methods that you can use, because you might have noticed that first, when we found the z-score, we could already make a conclusion. So this is saying we use the z-score to make our decision. Here, instead of drawing the picture of the z-score in the rejection region, we use the z-score to help us find the p-value. And then we compare our p-value with our significance level and let that help us make our decision. So you have two different ways you can make your decision. And then once you've decided to reject or fail to reject the null hypothesis, then you can restate your decision in non-technical terms. So here is our summary right here that you can use if that helps you. And of course, anytime we do hypothesis testing like this, there's always a chance that we could make some errors. So there are two different types of errors. They call them type 1 error and type 2 error. So the type 1 error is that you reject a null hypothesis, but it's true. A type 2 error is that you fail to reject a null hypothesis, but it was false. So what we're going to do is we're going to write down what the type 1 error and what the type 2 error would have been for that example that we just did. Okay, so the type 1 error is that you reject the null hypothesis. So you would reject that most users, internet users, use two-factor authentication and it's true, but they do. You reject it, but they do. The second type, type 2 error, is you fail to reject the null hypothesis. So you fail to reject that most users use two-factor authentication. And it is false. So I fail to reject it, but it's false. But they don't. Okay, those are the two types of errors that we have. So in this case, I did not reject the null hypothesis, so I'm definitely not at risk for a type 1 error. I did fail to reject the null hypothesis, so I could be at risk for a type 2 error if I did something wrong in my procedure. All right, so what we're going to do is we're going to take another example and we're going to walk our way through all of the steps so that we can try doing it again and see how we feel about it. All right, so this says a random sample of 130 human body temperatures has a mean of 98.25 degrees Fahrenheit and a standard deviation of 0.73 degrees Fahrenheit. Does the data indicate that the average body temperature for humans is different from 98.6 degrees? So step one is to identify the claim to be tested and express it in symbolic form. So they're talking about average body temperature. So they're talking about the mean of the population. So they're asking if the mean is different from 98.6 degrees. So they're saying, is mu different from 98.6? That's what they want to test. The symbolic form of the exact opposite of that, the symbolic form that the original claim is false, would be if it's not 98.6 degrees for the original claim, then if that's false, that means it is 98.6 degrees. So next we have to identify the null and alternative hypothesis, and we're going to do that by saying that the null hypothesis is what we get when we choose equality. So the null hypothesis is the one that has the equal sign. Mu is 98.6. The alternative hypothesis is the other one. So this is going to be mu is not 98.6. Now, before, in the previous problem, we had that the population proportion was greater than 0.5, and so we were looking at the right tail of our distribution. Here, if we're saying not equal to, then we're saying it's less than and greater than. It's not equal to, it's less than and greater than. So this means we're going to be looking at the left tail and the right tail. This is two-tailed. It's going to be important for a future step. Okay. Next, select the significance level. There's nothing in the problem that tells us what significance level to use. And so we're going to use alpha is 0.05. All right. Next is to identify the statistic from the sample that is relevant to the test. So we know that we're looking at a mean, and I'm going to look at a previous page on my notes so I can see that chart again. We know that we're looking at a mean, so we have two situations. One of the situations was where the standard deviation was not known. The other situation was where the standard deviation was known. Both of them ask either that you are told that it's a normal distribution or that you have a population, not a population, but that you have a sample size greater than 30. So we have a standard deviation that is known, and we do have a sample size that is greater than 30. So we are talking about a z-score. We are talking about a normal distribution and a z-score. So I'm going to go ahead and write that down. We have a population mean. We know the standard deviation, and n is greater than 30. So we're going to use a normal distribution and a z-score. Okay, so we're going to find the value of the test statistic. Technically, when we do this, we could only use the test statistic, only use the z-score, or we could use the z-score to find the p-value. But I'm going to do it both ways. Okay, so we know that one or the other could help us make our conclusion, but I'm going to do it both ways so that we can practice both through these notes. So I need x bar, mu, sigma, and n. X bar is 98.25. That is the mean temperature from the sample. The mean temperature from the population that we're testing is 98.6. The standard deviation is 0.73. And the number of temperatures in the sample was 130. So the z-score is going to be calculated by doing x bar minus mu 98.25 minus 98.6 divided by sigma over square root n, 0.73 over square root 130. Okay, so I'll go ahead and type this in on my calculator. 98.25 minus 98.6 over 0.73 divided by square root 130. Okay, the z-score is negative 5.47. Okay, so I'm going to draw my standard normal distribution. My alpha was 0.05, but I have that for two tails. And so I'm going to have a little bit on the left over here and a little bit on the right over here. And altogether, that has to add up to 0.05. So 0.05 divided by 2 is 0.025. So I can look back at my notes for my critical values here, or I can look at my standard normal distribution. So 0.025 probability oops, 0.025. It's right here. And that is at negative 1.96. That number should be familiar. It's something that we worked with before. So this critical number is negative 1.96. This critical number, if I were to find the other one, there is some symmetry there. So that's positive 1.96. And so that means that z-scores and these shaded regions are rejected. These are our rejected regions, our rejection regions. So negative 5.47 as a z-score is definitely over here in this negative region, which means that based on that test statistic, I know that I'm going to be rejecting the null hypothesis. I don't even really need the p-value. I just know I'm going to reject it based on this picture that I just drew. However, now, even though I already know my conclusion, I'm still going to show you guys how to find the p-value in this situation, just in case you decide that you would prefer the method of finding the p-value to finish your hypothesis test, as opposed to drawing this picture and working it out this way. So the probability that z is less than negative 5. Sorry, I forgot to write z. The probability that z is less than negative 5.47 is the probability that we're going to look for. And if you think back to the problem that we were working with, we were looking at the probability that mu is not 98.6 degrees. So we were two-tailed, left side and right side. So when we find this probability, to make sure that we're doing two tails, not just saying just the left side, we're going to take our probability and we're going to multiply it by 2. So I'm going to find the probability that z is less than negative 5.47, and then I'm going to double that because I'm going to represent the two tails from the situation. So I'm going to look at my standard normal distribution table. I'm going to look for a z-score of negative 5.47. It stops at negative 3.89. And it says z values less than negative 3.89 produce a probability of 0. And we just say 0, that's like a positive 0. It's a decimal that's very, very close to 0, but a little bit on the positive side. So, and they typically write this as 0 with a little star next to it. And so I'm going to say 0 times 2, and this is because we have two tails. And if we have a probability of basically 0 and we double it, we still have a probability of 0. All right, so when I have the p-value, my p-value is 0, my probability is 0. Now I compare this with the significance value, the significance level. and my significance level was 0.05. So I have the p-value is less than 0.05. And remember what we said about the p-value. We said if the p is low, the null must go. So since the p-value is lower than the significance level, that means that the null hypothesis has to go. It has to be rejected. So we chose two different reasons to reject it. One, because the z-score shows up in the rejection region, and two, because the p-value is low, so the null has to go. So our conclusion here is that we're going to reject the null hypothesis. And then we have to go ahead and write our sentence. So I'm going to go back and get my little diagram. Does the original problem claim the condition of equality? Was the original problem saying the average temperature is 98.6? And the answer is no, it wasn't saying that. It says, does the data indicate that the average body temperature for humans is different from 98.6? So equality was not being contained, so the answer is no. Do I reject the null hypothesis? Yes, I rejected the null hypothesis. And so I'm going to phrase it this way. I'm going to say there is sufficient evidence to support the claim that there is sufficient evidence to support the claim that the average body temperature is not 98.6 degrees Fahrenheit. Okay, so one thing I want you guys to notice is that as we are writing our conclusions here, our conclusions have not really been in the affirmative. We've said we reject the null hypothesis, we fail to reject the null hypothesis, there's sufficient evidence to support the claim that the average body temperature is not something, but we don't say definitively, we claim that the average body temperature is 98.6. So hypothesis testing is a little bit more about what you don't know as opposed to what you can accept to be true. It's about what you can prove to be false, if that makes sense. Okay, so let's go through and let's write down the type 1 error and the type 2 error for this situation, and then we'll be done. So type 1 error is that you reject a true null hypothesis. So this would be, we reject that the average body temp is 98.6 degrees. We reject a true null hypothesis. So we reject that the average body temp is 98.6 degrees, but it is. And a type 2 error would be you fail to reject a false null hypothesis. So we fail to reject the average body temp is 98.6. But it's not. And the type that I'm at risk for with my conclusion right here, we rejected the null hypothesis. So the one that we are at risk for if we made a mistake is that we did reject the null hypothesis. So we're at risk for a type 1 error if we made a mistake.